Well, good morning. So we are going to start talking about analog circuit design, and the first step in that is making sure that we understand the background of the devices and have a good understanding of the device physics behind the devices that we use. So in the next few lectures, we'll review that material, and then that leads us to the actual design of the circuits. So the first step in understanding the analog circuits is understanding semiconductor materials. So the question is really, what is a semiconductor? So what is a semiconductor? Anyone? Any thoughts? We're starting with a question. So we're talking about semiconductor materials, to be clear. And how do you define a semiconductor? Yes?
Somewhere between an insulator and a conductor.
Somewhere in between an insulator and conductor, right? So what do we mean by that? So let's think about what do we mean by conductivity or resistivity. So if you start with a very simple model, that's like the basic model of a material from an electrical standpoint. If you start with a slab of material, right? And then you make a perfect connection on one side and another perfect connection on the other side. And look at what we know from Ohm's law is that if you apply a voltage, there would be a current flowing, and that current, the ratio of that voltage to that current defines the resistance of this thing. And the resistance, though, if we know the dimensions of this thing, if it has a length L, a width W, and the thickness T, which basically corresponds to an area A, is given by rho L over A. Now, rho is what we call resistivity. And it's measured in units of ohms times meter. And L is the length, and A is the area, right? So why do we define it this way? Why don't we just write the resistance? The point of writing it this way is that you have these parameters separated. So this becomes a property of the material. This is independent of the shape. So we have gone from something that's shape-dependent, resistance, to a parameter that becomes independent of the shape, in this case, resistivity. And of course, conductivity is defined as 1 over resistivity. So this is conductivity. Now, why is it this way? Why does it look this way? So what is the intuition behind this? So think about it. If I take two of these slabs and put them in series, back to back, what do I expect my resistance to be? If I pass the same current, how much voltage do I get? If I pass the same current through this, I'll get the same amount of voltage I used to get across this one, and I get another one of the same value across the next one. And the sum of these two voltages is twice, so basically it means that my resistance really is doubled, which means that basically I have to be proportional to the length, right? The other thing that's important is that why is it inversely proportional to the area? By the same argument. So what if I take two of these and put them in parallel and apply the same voltage, right? If I apply the same voltage across two of these in parallel, then each one of them carries the same amount of current as it did now, but now you have two of them in parallel, so you have twice as much current. So your resistance is halved. So that's kind of like one way to think about them. You can put them in series and parallel, and that's the way the scaling works. But the key is really this resistivity, right? So, and what are the typical values of resistivity? So the resistivity, let's say for aluminum, is on the order of, does anyone know? Order of magnitude. It's on the order of 10 to the negative 8 ohm meters, right? Now, and aluminum is a conductor. I think everyone agrees that it's a conductor. It's a pretty good conductor. In fact, per unit mass or weight, it is the best conductor. Silver has a higher conductivity, but aluminum per unit mass is much lighter, and even better than copper in that sense, per unit mass. Now, the other thing is that how about an insulator? So let's say silicon dioxide, glass. Do we know what the conductivity or resistivity of that order of magnitude wise is? It's 10 to the 14 ohm meters. So you see there's a large difference between these things, right? It's about 22 orders of magnitude. And interestingly, both of them are extensively used in integrated circuit design, which is one of the focuses of this class. So what do we, so it's clear we call this a conductor, and it's clear that we call this an insulator, right? So if we kind of have some sort of a scale, so you can say, okay, so this is like 10 to the minus 4, and 10 to the 4 or 3. Stuff above that are insulators, right? And stuff below that are conductors. And of course, there's something down here, which is basically 0, which is a superconductor. And that exists too. Now, stuff in between, which are basically, you can say, poor insulators or poor conductors, sometimes you can call semiconductors. So this is a very high-level macroscopic viewpoint, right? This sounds somewhat arbitrary anyway, right? Doesn't it? It sounds like you're looking at something and saying, okay, well, I define this as conductor and define insulator. There's not really much sense to it, except for the fact that it's a practical matter. So that's a macroscopic view. So for us to develop a better sense, we need to really develop a microscopic view. We have to understand what happens at the microscopic level. And that's what we'll be spending the rest of today developing that. So at the end of today, hopefully, if we are efficient, we will be able to determine this in terms of microscopic properties of the material. So the rest of this lecture, really, and the rest of today's lecture, will be focused on arriving at this. So again, if you're efficient, at the end of that lecture, we will arrive at this number in a microscopic level. So we'll have to go through that process now. Any questions about the macroscopic level, why we are defining it, why we are doing it the way that we are doing it? No questions, all right? Feel free to ask questions. So from a microscopic level, what is the building block unit of objects, of things? What is it? Atoms, exactly. So, and what is the simplest atom we can think about? Let's start talking about that. Hydrogen, of course, right? So let's talk about start with the hydrogen atom. Now, I want to just warn you about something. This is not intended as a full coverage of semiconductor or solid-state physics. That's covered in different classes. We'll just be covering the simplest models that allow us to understand what we need to understand for circuit design. So this is not intended as a full lecture on deep solid-state physics or in that sense. So, but let's start with the hydrogen atom. So we know that a hydrogen atom consists of a proton with a positive charge, plus E, and an electron moving around it. Now, we know that this electron's trajectory is kind of like somewhat unclear. It has but there's so-called orbitals around it. There are some states basically where there are certain places where it has a higher probability of presence than other places. But we will deal with something that's even simpler than that to arrive at the things we want to arrive, which is basically Bohr's atomic model. And even before we start at that, we think about the basis of the quantum mechanics, really. What makes quantum mechanics quantum mechanics? What is the fundamental thing that has led to all of this more complex views of the quantum mechanics? It's the wave-particle duality. The fact that a particle behaves like a wave, and a wave can behave like a particle. It's that duality. And that duality is really captured by the so-called de Broglie wavelength, which basically says that for a particle with momentum p, you can associate a wavelength, so you can treat it like a wave, and the wave has a wavelength that's defined as the Planck's constant divided by that momentum. So this is the momentum, and this is Planck's constant. And Planck's constant is 6.62 times 10 to the negative 34 joule seconds. So it says that if I take this eraser, and if I throw it with a certain velocity, m times v of that, h divided by that, associates with the wavelength. So I can treat this like a wave with that wavelength. Now, why do we view this as a wave often frequently? Why, if I throw this at you, you would not view it as a wave and you view it as a particle or an object? Because if you think about this, this momentum is pretty large and this number is pretty small. So this wavelength becomes so small that essentially for all dimensions that we aren't concerned with, it's not going to matter. So you can actually view it as a particle. Now, but in a hydrogen atom, that may not be the case. So basically, you can imagine that you have the very basic model, let's say that like these planetary orbit movements, where the electron is moving with a momentum p and has a negative charge, negative e, around a trajectory. And the question is that if this electron is treated like a wave, what are the allowed trajectories? And from that, we'll calculate the allowed energies, and from that, we calculate some other parameters associated with that. So what condition, if this were a wave, do we need? But now, by the way, what does this wave represent? If this wave is there, and in quantum mechanics, sometimes you actually view it with the psi function, what does it represent? Probability, right? The wave function magnitude squared is going to represent the probability of the presence. That's one view. That's a very dominant view of the quantum mechanics of the presence. So if I want to have a significant presence in the vicinity of this circle, then what kind of property should this wave have? It should form the so-called quote-unquote standing wave, right? In the sense that the period should be such that it closes. Well, kind of. I didn't do a really good job on that, but something like that. So we want, if you have the circumference of this circle being an integer multiple of the wavelength, then this can sustain. So this would be one of those allowed trajectories or allowed paths. So what is that? What does that condition translate to? So what is the circumference of the circle? So let's say this is r. So it's going to be 2 pi r equals n times wavelength, which now is going to be n lambda, nh over p. So this is a condition for having a sustainable trajectory, or sustainable orbit, more accurately, for this. So this gives me gives us a relationship between the r and the p, the radius and the momentum. So now the question is, how can I determine what r and p are? Because I have two unknowns right now, right? And as such, I can't find out. So what is the other known thing in this whole equation? What keeps this electron going around the proton? What does it keep it here as opposed to just it flying off? What keeps the electron bounded? Yes, Nikhil. Right. It's the electrostatic attraction between a negative charge and a positive charge, right? And we know what that Coulombic force is, right? So that force is what? It's 1 over 4 pi epsilon naught. That Q1 times Q2, in this case it's going to be E squared, divided by R squared, right? So that's the force. Now, this force has to be equal to what for something to go in a circle? Classical mechanic, right? If I have a mass on a string and I start rotating it, the force on the string is determined by what? This is the so-called centrifugal force, right? Right? You have to maintain a certain centripetal force, essentially, to maintain that orbit. And what is that force? mv squared over r, exactly. So that's mv squared over r. Now, I want to express this in terms of momentum. So I multiply and divide by m. So I get m squared, v squared divided by mr. So I can write it as p squared over mr. So now you can see we have our second equation between p and r. So we have two equations and two unknowns between r and p. Everything else is known. m0 is the mass of the electron. It's called m0. Epsilon, so let's write these numbers. H we already have written down. Epsilon naught, does anyone remember? What's the permittivity? 8.85, 10 to the minus 12 farads per meter. We have also m0, the electronic mass. What is the electron mass? 9 times minus 31. Thank you. So that was very good. Now, so this is one of the things that I usually tell people, is that if you want to remember one of these two numbers, because a lot of times I ask people, so what's the mass of electron? You know, of course, both of them. But you say 9.1 times 10 to something. And that's a lot less useful than telling me it's 10 to the negative 30 or 10 to the negative 31 times some other number in the front, because at least now this is helpful. This is useful for something. This is not useful at all. So yeah, I mean 10 to the minus 30 roughly kilograms, but that's the mass. Okay, so we have the two equations, two unknowns, and we have to solve it. And we can solve them in different ways. One way to solve it is basically to notice that these two r's, one of the r's can cancel here. So I will rewrite these equations. This is a basic manipulation part. And okay, so then we will get 1 over 4 pi epsilon naught E squared over R equals P squared over M naught. So, and you can do various things. For example, I can take the R out from this one. So this is basic algebraic manipulation. I'm going to plug it into this guy. And what I will get is that 1 over 4 pi epsilon naught, let's say E squared. Let's absorb that into that fraction. And then you get 2 pi P over NH equals P squared over M naught. One of these P's cancel. So you get P equals M naught E squared. This 2 pi and 4 pi leave a 2 behind. So you have a 2 epsilon naught N, H divided by N, 1 over N. And then you can plug this back into the R equation to get your result. So you get NH over 2 pi times NH over 2 epsilon naught M0 E squared. If I haven't made a mistake, then basically it becomes, I think I may have made a mistake. So this is 1 over P. So it's 1 over that. So it's NH M0 E squared. So 2 epsilon naught divided by M0 E squared. Let me double check. I think I may have made a little mistake here. No, actually I haven't. No, that's good. So these twos cancel. I'm left with epsilon naught pi M0 E squared N squared H squared. So we have the R, let's write it this way, and P. We calculated these two. Now, what is the takeaway from this? I mean, the equation is just an equation. That's not particularly useful unless we have some meaning associated with it. The takeaway from this is this n, really, right? What does this n tell you? N is an integer, obviously, right? Because I didn't explicitly state it here. But n is an integer. Now, what does it mean to have an n in there, an integer number? It means that you cannot have any arbitrary values of p or r. So it's the quantization that's happening. Now, because of this wavelength nature of the wave-particle duality, you can see that both your momentum and your radius is quantized. It can only take certain values. It cannot take a continuum. Now, does it happen all the time? Is everything quantized? Or is the energy, let's say the momentum of an electron always quantized? No. What is the condition? What would need to happen for something to get quantized? Say again? A bound state, right? Which means that you have to have, that's exactly correct. You have to have a bound state for quantization to happen, which in simpler terms means what? About the total energy of the system, of the particle. For something to be bounded, what do we need to have happen? It has to have a total energy, negative total energy, right? So if the sum of its kinetic energy and potential energy has to be negative. If it's positive, it means that it's a free particle, essentially. Right? So that means that, and this is a bound electron, right? Because this is basically attached, quote unquote, attached to the particle. So let's calculate that total energy of this particle. So let's just open a little window here and say E total is, what is the E total? Is the potential energy plus the kinetic energy. Kinetic plus the potential. So what is the kinetic energy? What's the kinetic energy? 1/2 mv squared, or p squared over 2m. So it's p squared over 2m, and that part is positive because it's moving. And now, how about its potential energy? What is the potential energy? What is the potential involved here? What kind of potential do we have here? It's the electric potential, right? The electrostatic potential. And what is the potential energy of an electron and a proton, or a positive and negative charge at a distance r? It is negative 1 over 4 pi epsilon naught E squared over r, not r squared, because it's now energy. Right? So this is the total energy, but from this we can easily see, actually from here, we can easily see that this is p squared over m naught, and this is m naught too. So this is basically p squared over 2m naught minus p squared over m naught, which is what? Which is negative p squared over 2m naught. So we see that negative energy. We see the negative total energy, and it's a bounded particle. Right? So you can also express, now that we have this expression, we can also express it in those terms. So we can actually plug this into this guy, and what you will get is that you will get m squared e to the 4 divided by 8 epsilon naught squared h naught squared 1 over n naught squared, n squared. There's no h naught. So h squared and n squared. Sorry, not h. And this is the quantity we can calculate. We have all the numbers. We know E. Well, I didn't write E here, but 1.6 times 10 to the negative 16. I'm sorry, 19. 19 coulombs. 1.6 times to the negative 19. And so you plug these numbers in. You take the calculator. You will get something like, I think you get 7.17 10 to the minus 18 joules, or in electron volts, that's written as 13.6 electron volts divided by n squared. So this is some of the basics of modern physics, basics of quantum mechanics. So what you see is that you have these energy states that have these negative energies, and they're quantized energy levels. And this is what gives rise to, for example, the spectral bands of hydrogen or other atoms. And this was the thing that led to all of these things. So basically, they were observing these energy levels, and they were trying to find out what's going on, why they have this discrete energy levels, and they came up with formulas, which basically were in the form of 1 over n squared minus 1 over m squared for m and n integer numbers. And then they saw these things, and eventually, kind of like when Niels Bohr came and said, okay, if we have this is at the turn of the 20th century, so basically they came up with this model and said, okay, well, this is what's happening, these are the energy levels, and if these are the energy levels, then the transition from one energy level to another one would correspond to a release of a photon with that wavelength associated with that energy, and so on and so forth, and then the rest of the quantum mechanics ensued. So this viewpoint, why did we develop it? Okay, so let's think about it. So what it is, really, if you think about these energy levels are, so think about an atom, right? So this is energy being 0. Now, so the lowest energy level is what, according to that equation, for a hydrogen atom? What is the lowest energy level? It's negative, when n is equal 1, right? So it would be negative 13.6 eV. Negative 13.6 electron volts is down here. So, and then what's the next one up? I think it's just 3.4. It's just this divided by 4. 3.4 eV. And the next one up is, so this is a little higher actually. The next one up is negative 1.5. Again, this thing divided by 9. And then you have another one, and then you have a whole bunch here, right? And then what happens above? What if your energy is positive? What happens? Okay. what are the energy levels when the energy is positive? It's unbound. So basically all of them are allowed. So all of these are allowed energy states. It's a continuum of energy levels. So yeah, this is the basic stuff probably most of you have seen already. And there's this association with the atom, right? So this is basically the hydrogen and discrete energy levels of a hydrogen atom. Now, if I had instead of a hydrogen atom which has one electron, one positive E, I can also could have potentially a positive ZE, right? I mean, if I had a larger nucleus with energy levels, what happens is that these energy levels will not remain the same. So this is for 1E, let's say, plus E. But now let's say I have another atom, but now this time instead of 1E, basically I have plus ZE. So I have some energy levels, which would be numerically different from these, and there would be a continuum of energy for positive energies. And that's the way the energy levels will look like, right? So there would be some energy levels. Now, the key part to this discussion is that, now what happens if I have another atom, just like that, sitting on the other side? What would the energy levels be? So if these two atoms are far apart, right, each one of them will have similar energy levels, presumably, right? As they come closer, though, what happens? So if I take that atom and put it here, so what would happen to the energy level? So let's say they are pretty close to each other. Does anyone have a thought on what would happen to the energy levels and why? Any thoughts? Does anything have to happen? Do the energy levels remain the same? If I take these two nuclei and put them right next to each other, presumably I can do that, let's say, would everything remain the same? Or would something change? Pauli exclusion principle, right? What does Pauli exclusion principle say?
You can't have two different fermions occupying the same.
Right. And electrons being fermions, basically you could say that you cannot have the same quantum numbers. All the quantum numbers cannot be identical when you have two particles coming together. So what would happen to the energy levels? When you said you run into Pauli exclusion principle, which is actually correct. And then what do you think will happen to the energy levels? Because now these two things are occupying essentially the same spatial area, right? And now what would happen to the energy levels? Can they be the same? No. So the energy levels have to become slightly different, right? So now each one of them will split. Remember, by the way, each one of these energy levels can take two electrons because one of the quantum numbers is spin. So it can have an up spin or down spin. But this is independent of that. This has nothing to do with that. So this energy level, for example, becomes two energy levels, two very slightly different energy levels. And here the same thing. Oops, not crossing. And so on and so forth. So now you have two energy levels that are split slightly different, and they call it the degeneracy of the energy level. So the question that, one question that arises at this point is that, wait a second, at what distance, so let me ask you a question, at what distance does Pauli exclusion principle kick in? Is it like it happening at 1 kilometer? Is it happening at 1 meter? Is it happening at 1 micron? Is it happening at 1 angstrom? What is it? When does it kick in? So what's the answer? What are your thoughts? When does Pauli exclusion principle become important? When does it turn on? So the Pauli exclusion principle is sleeping, say, oh, wait a second, no, I'm too close now I have to turn on. Does it work that way? Yes? Okay, so does Pauli exclusion principle say that the two atoms cannot share the same quantum numbers or have the same state, exact same state, if the spacing is comparable to x? No, that would not be a good kind of principle, right? It would be a funny principle. So what is the answer? What is the answer? Why do I say, okay, there's no degeneracy, but when they are close, there's a degeneracy? This is more of a little bit of a more fundamental question, but what is the answer?
Do you just not notice it?
Speak up, sorry.
Do you just not notice it?
She said, okay, it's an interesting thing. She said, just not notice it when they're far apart. That's actually correct. That's actually a very good answer. It's always in action. Pauli exclusion principle is always there. No two atoms in the universe share the exact same quantum numbers. But the farther they are, the less different they will be. So the degeneracy is so small that you do not notice it, particularly if you're not at 0 Kelvin. Because then, as we'll see later on, there's all sorts of thermal effects and all those things, so it will be buried in those things, so you actually do not see it. At some point, it becomes observable, and since we are never really at 0 Kelvin, based on the third law of thermodynamics, we never see them for things that are, we don't see them for things that are far apart. Otherwise, two atoms across the universe will have some degeneracy induced because of that. So it's just a question of how far apart are they before they are noticeable, this degeneracy. So that was a really good answer. Yeah. Is it clear? So now, so that's part of the discussion. But really, what we are trying to find out is not just two atoms. In solid state systems, the word solid state means that you're dealing with a solid, which basically means that you're dealing with a very large number of atoms. So what happens if I bring a large number of atoms together? If I have a whole bunch of these things, and I start making a crystal lattice, right? So I have atoms in 3 dimensions forming a crystal lattice. Well, one too many. And so on. So what would happen? So let's say I take atoms and start them far apart from each other and with uniform spacing, and I just shrink this 3-dimensional uniform spacing of the atoms and bring them closer and closer. So imagine this whole thing scaling down and becoming smaller and smaller. As that happens, what happens to the energy bands or energy levels? So now you have multiple atoms, so you have multiple energy levels, right? And the closer you bring them to each other, the more degeneracy you notice. So there are multiple energy bands for each one of them, multiple energy levels, for each one of them. To the point that at some level, they have so many atoms that are degenerate that they create the so-called energy bands. So it looks like a full band where you can take any energy within that band. So these energy levels, because of the Pauli exclusion principle, turn into energy bands. So these would be allowed bands and there would be forbidden bands or band gaps in the system. So you can actually look at it a little bit more clearly. So let's move on to the next word. And here's what we are going to be doing. So when we actually have this energy band, so let's say we are building a crystal lattice. So let's look at the energy levels for a particular atom, let's say a carbon atom. And let's say this is atomic spacing. So you are making a face center cubic crystal, the diamond essentially. You're making the diamond as you bring the carbons close to each other in a 3-dimensional arrangement. And the question is, what happens to the energy level? So carbon, what's the carbon atomic number? What's the atomic number of carbon? 6, right? Carbon is the 6th element. So how many electrons does it have? As a result, it has 6 electrons. Now, so a single carbon atom, so what are the orbitals? What are the orbitals that we are familiar from chemistry with? This is the 1s, then you have the 2s, and then you have the 2p, which is really py, px, py, pz. So how many, for n atoms, how many available states are in 1s? So 2n, right? For each atom you have 2 because of the spin, because you have 2. So basically you get 2n states available for you, for n atoms. And how about 2s? Same deal, right? You get 2n states. And how about 2p? P's there are 3 really, px, py, pz. So it's 6n states available. So this is when the atoms are really far apart from each other. So Pauli exclusion principle is still in action, but the effect is, the degeneracy is negligible. You don't see it. Now, as you're bringing them closer, as we argued, this degeneracy becomes more visible. So you get these bands. Now, here, one of the interesting things that happens is that there's a degeneracy, so there's opening, and then there's a mixing. There's a blending of this thing, and then there's a splitting. And this is the way the band diagram looks. I put this too far out here. Okay. So something like this happens. Again, so these are where the allowed, and this is the actual, let's say, diamond spacing, diamond lattice spacing. So at this point, you have these energy bands. So what happens here is that at this spacing, you have 4 n states here. These are still the 2 n states that you have from 1s, and then you have 4 n states here. Now, what has happened in the chemistry language, in the language of chemistry? What is happening here? This has a name. Does anyone remember what that name is? It's called hybridization. This is in particular the sp3 hybridization, which basically corresponds to things at the tip of a tetrahedral with angles of 109.5 degrees. And that's the spacing you have in a carbon lattice, a diamond lattice, sorry, which is a carbon lattice, what's three-dimensional carbon lattice. So this is the sp3 hybridization. You may be familiar with those orbitals that they draw, the 4. So this is what happens with carbon, for example, CH4, right? Methane has this hybridization. The 4 hydrogens sitting at the ends of this thing, so you have a CH4. That's the hybridization that happens. So this is basically what's happening here. And now let's see, how many electrons did we have in this case for the carbon? Total electrons per atom. How many electrons we had per atom? 6, right? So for n atoms, we had 6n. So at 0 Kelvin, so this is at 0 Kelvin, the absolute 0. There's no thermal energy. Let's say, make it a little bit cooler at 0 Kelvin, with blue. So what do we have? What is filled and what is empty? So of course, at 0 Kelvin, there's no thermal energy, so everything will fill up from the lowest energy states. So these guys are completely full. These guys are completely full, right? So this is full, full. And we've used everything, you've used up everything. So these are completely empty. So here, what you have these 2 energy bands that are completely full, and this energy band that's completely empty. Now, what does that mean? What does it do from a perspective of conductivity behavior? So another way to think about this, another way to visualize this, which is a common way for us, let me just reproduce this here to the extent that I can. This is the 109.5 degrees. Now, is that you can think about them as basically, you can view it here, because you really don't see carbon in this position. I mean, this is more of a thought experiment, if you will. Right? You're taking this carbon atoms and bringing it. If you have a diamond lattice, the spacing is going to be here. It's not going to be there. Right? So you can look at this energy band diagram across here and show it like that. So you can actually say, look, I have this band, this point. So here I have the so-called the valence band. And here what we call the conduction band. So this is a band and this is another band, conduction. Now, this one is completely full. And we don't worry about this because this is such a lower energy state. It requires a lot more energy to release electrons from here. So you have this one that's completely empty, this band, and this band that's completely full. Now, going forward, a lot of times, we just show the edge of these 2 bands, the conduction band and the valence band. And what we are doing, basically, we are showing this edge of the upper edge of the valence band and the lower edge of the conduction band. Because we know there's a lot of states above it and a lot of states below it. So this perspective also, if you think about it, if I try to planarize the view of the lattice, so this is not the way diamond actually looks, but this is kind of a visual, easy thing to visualize and draw, is something like this. So you can actually say, these are my atoms, and I'm forming a lattice. So these are my carbon atoms, these little circles. Okay? And you have these things. Now, what do these represent? What do these two lines, I mean, you've seen this probably in chemistry. Yes?
I have 2 questions.
Sure, do you have questions? Good.
So is N the number of carbon atoms?
Is the number of carbon atoms?
Not just 2 carbon atoms?
No, I'm talking about n carbon atoms, but remember each one of these states can take 2 electrons for 2 different spins, right? Each orbital can take an up spin and down spin. So for n atom, you have 2 n available states here, you have 2 n 2s states, and you have 6 n because there are 3 of them really, p, x, p, y, p, z. So it's a total of and if I have n atoms, I have 6 n electrons. So 2n of it goes there, and 4n of it goes there. Right? So my accounting should be okay.
And then,
Yeah.
how does the x-axis, the atomic spacing, compare with like the average atomic radius?
Oh, okay. So the atomic space of diamond, if I'm not mistaken, is I think 0.15 nanometer, 1.5 angstrom. But I can look it up. But I think I had it written here. But yes, it's 1.5 angstrom. Yes, it's 1.5 angstrom for the diamond lattice. So it's basically the spacing of 2 adjacent atoms is 1.5 angstroms, or 0.14, or 150 picometers. Right? It's a good question. Yeah, these numbers are important because you want to develop a feel for what they are like. All right. Any other questions? All right. Okay, so, but in this picture, so what are these lines? What do these lines represent? I mean, what kind of bond, what kind of atomic bond do they form when you have carbon? Let's say if you, in a diamond lattice, what kind of bond do you have? Covalent bond, right? Is covalent bond a strong bond or a weak bond? It's a strong bond, right? It's a very strong bond. And that's why diamond is so hard. That's one of the reasons. Of course, there are a lot of other things that have strong bonds. But why is diamond so hard? Why is diamond one of the hardest materials? Why is it? What is the second thing that makes it really hard? I mean, intuitively. So that.
Nice crystal lattice.
Well, it's a nice crystal lattice, but there are a lot of other nice crystal lattices. I mean, just actually identical ones. For example, silicon. When we get, the reason we are using carbon is basically that it's a surrogate for silicon. Because silicon has exactly the same thing. All the column 4 elements, which are very important to us as semiconductors, as we'll see, have this lattice. But so yes, that is correct, what you said. That's one of the elements. But there's another thing about carbon that makes it, that diamond that makes it very hard. Carbon atom is the smallest that forms this kind of lattice. So it's very compact and very small atom. So these bonds are pretty close to the nuclei, so they're very strong. If you're in the outer shells of an atom, the attractive force is less effective, I mean, loosely speaking, and therefore these are the strongest bonds of all bonds that you can form. These are the strongest covalent bonds. These are tiny atoms, tightly packed, close to each other, energetically very strong. So that's what makes diamond so special. Diamond actually is special in so many different ways. Not the fact that it's artificially highly priced item because there's a monopoly on it and they throw away 90% of it. The main reason is that it's the best thermal conductor out there by a large factor. If you're really looking for a really good thermal conductor, diamond is your thing, especially if you are looking for something that's an insulator too. And also it has some very interesting optical properties which gives it its brilliance. It has very high index of refraction. So there are good reasons for diamond to be special. But anyhow, so these lines really represent a pair of electrons that are basically shared. These represent covalent bonds. right? So in this picture, this is a simplistic picture, but it gives us an essence of what's happening. So what's really happening is that you have these sp3 orbitals, and then there's another carbon atom with an sp3 orbital, so they are forming bonds here. So this is basically the two up and down spin atoms forming a covalent bond. So that's what that really represents, right? So when you have something like this, now is this a, what do you think this is? Do you think this is a good conductor? Do you think it's a good insulator? Do you think it's a bad conductor, bad insulator? What is it? What is this material in its current form? Let's say at 0 Kelvin. It's an insulator, right? Why is that? Yes. So what happens is that you can think about it. These are really nicely sitting there, happy. They form very strong bonds, just like everyone is paired up. Nothing's going to happen, right? Another way to view it is that you have a full valence band and an empty conduction band. So an analogy which I actually like, which I think is a reasonably apt analogy as the analogies go, is the analogy of two water-filled tubes. So think about two tubes. There's this tube, the lower tube, and upper tube. So imagine these are tubes, glass tubes, just because they're not glass tubes. But so let's say this one is completely filled with water, and this is completely empty, right? If I start tilting them, applying gravitational potential, right, would there be any net movement of water? No, because these are full. This is full. There's no empty place to go, and there's no water in the top one, so nothing's going to happen. Right? So now, if I take a droplet from this one to that one, put in there, something interesting is going to happen, which we're going to discuss. But as is, there's no net movement of water. So the same thing goes with electric potential. So if I apply electric potential, there are no free electrons here to move in this conduction band, and there's no place for these electrons to go, because everything is filled. So yeah, they can swap space, but that's not net current. They would be constantly swapping places, but there's no net current to flow. So there's no empty state here, and there's no free electron here. So this is a really good insulator at 0 Kelvin. Even above that, it's pretty good insulator, as we'll discuss in a second. So what determines the resist? What are the things that determine the resistivity of the material? Let's at least qualitatively now, and we'll make it quantitative in a few minutes. But qualitatively, what are the things that determine if something? So if I show you a band diagram with the electrons in it, can you tell me if it's a good conductor, good insulator, bad insulator, et cetera? So let's go through this exercise and see if we can do that. So let's say I start with something like that. So I have a valence band here that's completely full, and a conduction band that's empty, and they are pretty far apart. Is this a good conductor, good insulator, bad conductor, bad insulator, superconductor, whatever? So what is this from this perspective? What is it? I mean, this is similar to what we were talking about, right? This is an insulator, right? So this is an insulator because of what we just discussed. So the band gap is large, this band, and we'll see why this matters in a second. Now, what if I had a partially filled conduction band? Say here, I had some electrons here. Now, is this a good, what kind of material is this? What is it? It's a metal. It's a conductor. It's most likely a metal, but it's definitely a conductor. Because these electrons, there's a bunch of electrons here, and there's places for them to go. There's room for them, so they can go wherever they want. It's like if you take the water-filled tubes analogy, what it is that you have basically the lower tube is completely full, but the upper tube is partially full. You do this, the water goes down, accumulates down here, right? You do this, water goes down here. So this is the conductor. Now, so these are kind of like simpler one. Or what if there's no band gap? So again, which is similar to saying something similar as that. I mean, it's essentially the same thing. So let's say, for example, you have overlapping bands, and then you have some electrons filling up these things. Sure, still a conductor, right? Now, what if I had a band gap, but the band gap was smaller? How about this situation? What can you say about that? Would that matter if the band gap was smaller? Would it matter at some? So it appears like I'm still having no room here and no charge carriers there, right? So it appears that this should not matter. And you're right. I mean, if it doesn't matter at 0 Kelvin, 0 Kelvin being your clue. Now, what if you're above 0 Kelvin? What if you're at room temperature or at some other temperature? What can happen? What would happen? If you have thermal energy, yeah, there would be some electrons that can actually overcome this band. There would be some electrons that would have sufficient energy, because the energy distribution of these things, as we'll see later on, are really dictated by the Fermi-Dirac distribution. But even if you think about a simplified Boltzmann distribution, what happens is that every so often you will find a hot enough electron that would jump up from here, go there. So this electron is there, free, and it can move around. And in this viewpoint, in this picture that we had up there, that corresponds to a simplified view of thinking about, let's say, so let's redo this quickly. Again, you may have already seen this picture, but it's okay. It basically corresponds to what in this picture? This process, which is called, by the way, thermal generation. Speak up then. Yes, a bond breaks, right? So this one breaks, and an electron is freed. So an electron is free. Now this electron can move around. Now, in addition to the bond breaking and electron being free, there's something else that's happened, right? Now there's a hole, there's a gap, there's something missing there, right? Well, my color code is messed up. Okay. So what is missing there? There's a missing bond. But now this area, in this spatial area, is it still neutral electrically? No, it's positively charged, right? So this whole area has a positive charge, which is represented by this empty space, which is what we call a hole, right? An electron and a hole. So we have created a pair of electron and hole. Now this electron can free up and then move around. And now the same way, this hole can also move around. How can this hole move around? You say, well, wait a second, this is a broken bond. How can it move around? Does it move around? It does. Why does it move around? How does it move around? What happens in this process? Well, second? Well, a straight electron, if a straight electron comes in, it can form a bond, right? So they will both disappear. That's a recombination process, which we'll talk about in a second. But even in the absence of that, this thing can move around. Even in the absence of a free electron, this thing can move around. How would it move around?
One of the neighboring bonds.
Correct. One of the neighboring bonds. I mean, I like the way you described it, which is better than the way I was about to describe it. You say one of the neighboring bonds shifts to this thing. I was about to say, well, you break a bond and you form a new one. But I like that shifting because that implies a gradual transition. So what it does essentially is that now this positively charged area is here. Now, you may say, well, wait a second, these are covalent bonds. These are hard to break. So this would require a lot of energy, so moving of this thing should be very difficult. Not so. Because you already you're breaking a bond, but you're forming a new bond. Somewhat similar to what happens in quantum mechanics tunneling, right? You go from one energy state to another energy state that's equivalent. If there's a barrier that's very small, you can always go across. So breaking of this bond and forming a new one is a lot easier than just forming a new or breaking a bond without forming a new one. And that's why this thing can also be quite mobile, this hole. Now, the analogy, again, to going to our water-filled analogy, tubes, water-filled tube analogy, I guess, is that now you've taken a droplet, a little bit of water from this lower tube and put it in the upper tube now. On the upper tube, you have a droplet, right? So you move it around, the droplet goes left, right, etc. But now also the bubble moves, right? But the bubble moves in the opposite direction of the gravity, if you think about it, right? So if I point it this way, the bubble goes there. So the bubble, in that case, acts like a negative mass particle. And here, this acts like a positive charged particle. Right? So that's the analogy. Now, and again, to take that analogy again to the extreme, I mean, analogies can be very challenging and potentially problematic. But if you think about it, which one moves more easily? The bubble, if I do this, which one moves faster? Let's say the bubble and the droplet are right in the middle, and I start tilting it. Which one gets to the end faster? Does the droplet get here faster or the bubble gets up there faster? The droplet probably moves faster, right? Because the bubble is also experiencing all the drag force of the water. And the same thing happens to be true about holes and electrons. The electrons are more mobile than holes. They have more mobility. Again, this is an analogy just to think about it, a way of remembering things. But the same way that you can, if you think about that analogy, there are two ways to really, at least two ways to deal with that droplet, right? One of the deals to deal with that droplet is to account for the movement of every water molecule in that tube. Right? If you think about every water molecule in that tube, you can actually think about it and say, yes, you know, I can write all the hydrodynamic equations associated with that, and this is the surface tension of the bubble, et cetera, et cetera. It becomes pretty darn complicated. Right? That would be equivalent to trying to model this opening, this gap in state, with modeling all the electrons that are here. There's another way to think about it and say, well, I can treat it like approximate it as a negatively charged particle experiencing some drag force. And that would be an easier way. And that would be what basically we would be doing when we deal with these holes. So now you have these holes and electrons. But now you generate these holes and electrons. So going back to the original question we started with, which is this a conductor? Is this a good conductor, bad conductor, good insulator, bad insulator? Now, what's the answer? Somewhere in between, yeah. The really correct answer is to ask me a question. Say, well, at what temperature? And what is the band gap, right? Because I didn't give you any quantitative measures. I asked you a quantitative, something that requires some quantitative assessment of something. So you really need to ask me, say, what do you mean? What is this height? What is how many electron volts? What is the temperature? And at certain temperature, at hot enough temperatures, there would be enough of these things. So these guys can carry current, and these guys can carry current, and that would be what would be responsible for conductivity. At 0 Kelvin, yes, it's not a conductor. Okay, so now the other thing is okay. So one more thing before we take a quick break here is. This generation process, this electron hole pair generation process, if it keeps going on, what will happen? There will be more electrons and more holes, right? So is that what's going to happen in steady state? Would we just create more electrons and more holes, more electrons and more holes, when more electrons and more holes, and just like what happens? So there would be a reverse process, recombination, right? In the sense that if you have way too many electrons and way too many holes, every so often, an electron that may have originated somewhere else may come in and recombine with a hole that came from a different electron. So this may go here, this may go there. And in steady state, by definition of steady state, we should have one thing, which is the rate of recombination and the rate of generation have to be equal in steady state. Otherwise, by definition, you're not in steady state. Either you're generating more than you're recombining, or you're recombining more than you're losing more than you're winning, or you're winning more than you're losing, right? So if it's even, then it means that the two rates has to be. So the rate of recombination has to be equal to the rate of generation. Okay, so let's take a quick break. And when we come back, we'll continue.